50. There are, in fact, 50 or possibly more options if you are interested in using Spatial SQL to perform spatial analytics and store spatial data. That's a lot of different choices, and it's hard to decide and know what specific tools do what things well. And that's what this video is going to do. We are going to take a deep dive into the landscape of spatial databases, data warehouses, processing tools, and analytics engines to help you understand which tools make the most sense for you and how to use them. So the way we're going to structure this is actually look at it through a few different categories of database to help you understand how these things are grouped together. And then at the end of the video, what I'll do is I'll actually take all of that information and rank them on a matrix scale, talking about scalability and then analytics versus transactional workflows. Now, to just define what I'm talking about when I'm talking about analytics versus transactional is what you would think of in a traditional database. There is some event or record that takes place and you're inserting that into the database. It's also very good for retrieving very specific snippets of data. Analytical, on the other hand, is looking at aggregate or large groups of data and asking bigger questions. Maybe what's the min or the max across a specific set of data, grouping it by a date range or anything like that, or in the spatial context, doing large-scale spatial aggregates, spatial joins, k-nearest neighbor queries, and things like that. Now we're going to take a look at 6 different categories of database data warehouses. Let's just call them spatial SQL tools to make that a little bit easier from this point forward. So those 6 categories include relational databases, things like Postgres, MySQL, tools like that you would think of when you're adding transactional databases. Next, we're going to take a look at is data warehouses. Those are tools that store large amounts of data and allow you to add analytical queries onto them. So that's things like BigQuery or Snowflake or Redshift. Next, we'll take a look at Spark-based systems or distributed computing systems. That's tools like Apache Sedona, Wherobots, Databricks, and more. From there, we're going to take a look at distributed query engines, which is a little bit different than these distributed Spark tools that we're talking about. So that's Trino, PrestoDB, and other tools like that. We'll also take a quick look at GPU-accelerated databases. Tools like that are Heavy AI and others. And then finally, we'll take a look at other tools that include spatial capabilities that kind of don't really fit into any of these categories, but are ones that are good to be aware of. Okay, let's start with our relational databases, and we're going to start with the big one, which is PostGIS. Now, if you're not familiar, PostGIS is a spatial extension of the PostgreSQL database system that allows you to add spatial capabilities onto the regular database and do a lot of different things with it. This has sort of been the one that's been around the longest. It has the most spatial functionality, and it has lots of other extensions that go around it. Things like PG routing for routing questions. You can do geocoding, and frankly, the entire Postgres ecosystem is growing so rapidly that there's so many other things you can bolt onto that. One good example of this is a vector database system. That's not the vector data that we traditionally think of in Geospatial, but actually using that to store text-based data for large language models, things ChatGPT and tools like that. At its core, Postgres and by association PostGIS is a transactional database. That means that it's very, very good at inserting and adding records or looking up specific records at different times. So let's think of an example where you're in a store, right? And there's a transaction that's taking place. Someone is swiping their credit card, buying some items. Postgres, and by turn PostGIS, is very good at taking that information and quickly inserting it, keeping a record of that, allowing you to look up and go backwards and forwards and things like that to actually understand what's happening with that data. Now, it's not to say that you can't use PostGIS to do analytical queries. I mean, I wrote a whole book that basically covers all of that. But there are certain limitations because Postgres and PostGIS is basically a coupled compute and storage toolkit. So the storage, where you actually keep your data, and the compute, which is the computing power to process that data, is stored in the same place. But basically, if you need more power, you need to add more computing power to that. There's no way to kind of exponentially scale that or grow it outwards. Now, there are some tools that try to do that and do distributed Postgres. That's a little bit outside the scope for this video, but just so you know, that's kind of how the compute infrastructure is set up. All that said, PostGIS is probably the most dominant spatial database that's out there. You can certainly look at others that I'll talk about here, like MySQL, MariaDB, even into like SQLite SQLite, SpatiaLite, things like that. But PostGIS has been around for a very long time. It has the largest set of functions, and it's been used in so many different applications. Now, I mentioned tools like MySQL. There you can even look at Microsoft SQL Server, MariaDB, which is basically an open source fork of MySQL, which also have spatial capabilities in them, very similar to what Postgres is. There are less functionality or less functions that you can use there. But all that said, if you do have access to these databases or you're using them in your different systems, you can use spatial functionality within those as well. Now, of course, I also want to touch on SQLite or SpatiaLite. SQLite is claims to be like the most popular database in the world. It's very, very small footprint. Like it takes only like a very small amount of storage to actually store it and run it. And it's frankly running on so many different things like apps on your phone and different things in your computer and stuff like that, where it needs some sort of very lightweight database just to do something in a very small context, basically contained to you or that application or something like that. It's not connecting to like a massive database somewhere else. You probably have come across this if you've used like a SpatiaLite, database in a Jupyter notebook before, or you may have seen it in GDAL and some of the functionalities in the Ogre to Ogre toolkit that allow you to actually write SQL queries and translate your data that way. So it's kind of doing it in process for that very specific thing. So it's a really nice toolkit, super lightweight, but I wouldn't rely on it for like, production use cases or anything like that. So on the flip side of this, there are a bunch of commercial databases. These are primarily like open source tools that I've talked about. There's tools like Oracle Database and Oracle Spatial, tools within the Oracle system, Microsoft SQL Server, and then some of the kind of original OGs of spatial databases, IBM DB2, Informix Spatial Data Blade. Those are ones that kind of, I think they got acquired a few times. Ultimately, they ended up in IBM. But those are some of the original spatial databases. So if you look at this timeline here, it kind of walks through some of the progressions of all these different toolkits. But those were some of the original ones. And these are all, kind of similar things. They have varying sets of spatial functionality that they cover. So it depends on what's in each one. But relational databases that allow you to do this very similar transactional things that I've been talking about so far. So before I move on to data warehouses, which kind of fall in this analytical processing, there is one very honorable mention that kind of falls in the middle, which is, of course, DuckDB. And I've talked a lot about DuckDB, and what I think is probably the one of the most remarkable things about it is that it's so small to install and use on your computer or even into large-scale cloud processing systems and expanding it from there. But it's so easy to set up. You can read simple files, but the most important thing is it does analytical queries. Now, if you look at DuckDB, it kind of is equated to the analytical version of SQLite. And that's because it's very lightweight and easy to install and very quick and easy to use, but focusing on analytical queries. Analytical queries want you to look at specific columns of data and understand, trends or things happening across that, maybe averages or rolling averages, or, if you think in a spatial context, a spatial join and something like that. And that's what DuckDB does really, really well, is those analytical queries. And there's a number of reasons for this without getting too much into the weeds here, but it does columnar data support, which means instead of storing data in rows, as you see here, it stores them into columns, and columns have a few advantages. Number one, if I'm running an analytical query and I just select the columns I need, I could ignore the rest of the data set. In a transactional database, I still have to look at all those individual rows. On top of that, I can have some indexing within there. I can, kind of remove data or parts of it and store it more efficiently, specifically in the Parquet or GeoParquet file format. And then I think what's really interesting is the ability to look at chunks of rows. So let's imagine that I want to get the average or the sum of, transactions by every single day, or maybe grouped by location if you're running a retail operation, something like that. What I can do is that a chunk of rows within that column can store some summary statistics, just like you would think of for a raster data set. Summary statistics would be across 10 or 100 or 5, whatever rows there are. Here's in this chunk, there's that 5, the average for those 5 rows on that specific column. Now, instead of adding every single column up, it can take those chunks or even look at those parts of the data set and just pull those out and do the averages much, much faster, which is why you can see operations running so quickly on that type of operation. Like I said, DuckDB is super portable. You can run it in Python. You can run it on your command line. You can run it in an application. You can run it on the web and in, sort of in your browser as well. So there's so many places to do that. And then services like MotherDuck actually help you scale that into a cloud ecosystem, add, different security, storage, all these different pieces into that. So add basically getting close to what a data warehouse functionality is, but with DuckDB as the backend support. And DuckDB is such a maintained and organized project. That's kind of why I fell in love with it. It was just so easy to use and do some basic things on my laptop. Okay, so let's jump into data warehouses. Now, data warehousing has been around for a long time. It's the ability to store large amounts of data, be it any data that is being collected, usually like machine generated data, things like logs or, stuff coming out of who knows what it is, but machine generated data that you may want to analyze at some time. And data warehouses have been collecting that and allow you to analyze that sort of data in specific chunks or in specific groupings or, create reports and stuff like that. So that's why these tools like BigQuery, Amazon Redshift, Snowflake, even Azure Synapse Analytics have been created. It allows you to collect large amounts of data, query that very efficiently, and it has a lot of the same properties as the DuckDB as an analytical database. Many of them have the same columnar storage type of setup. They use partitioning, which is basically grouping your data or splitting it up strategically so you can just look at chunks of data a little bit faster. And what's most important is the distributed computing component within that. I should say distributed computing plus this separation of storage and compute. So let's break those two terms apart. When I talk about the separation of storage and compute in Postgres, everything is together, both the storage where the actual, the bytes of data are stored, and then the CPU processing or the computer processing that actually runs the queries that you need. So in a distributed ecosystem, what's happening is that you are keeping your storage separate and the query engine is retrieving the data it needs to run that query at a specific time. So if you think of a normal warehouse, if you're walking into Costco or one of the big box stores, things are organized into different rows. And in those rows, there's different types of things. That might be, food in this aisle, or more specifically, there might be canned items. And the next one, there's cereal. The next one's there's frozen, so on and so forth. Very much in the same context of a warehouse, you might store things and organize them by category or date. And that's kind of an easy way to think about partitions. It's very big oversimplification, but that's kind of what's happening there. And a data warehouse says, okay, I'm running this query. I just need to grab this chunk of data from these rows, or if you think of not rows, but these actual, parts of the data or partitions, as it were. So that's what's happening with the storage. Now, the compute is basically, as that query engine is running, it says, I'm going to need X amount of computing power to run this query. And different systems do this differently. Snowflake allows you to basically pick a sizing of compute, and you have access to that. And when you run that query, it will basically bill against that for that specific size. You can go up in scale and choose your tier of size that you want. So higher tiers run faster, lower tiers run slower. But it picks you, kind of helps you pick that size. Tools like BigQuery basically remove that decision making from you, and you can kind of, it allows you just to run the query and it will figure that out for you. Now, generally in cloud services, the more that decision making is removed from you, the higher the cost is going to be, because you're effectively, the cloud service is doing that for you, and that's part of what you're paying for. So that's something to think about in each of these different scenarios, what you're paying for and how those things work. But that's what a data warehouse does at the end of the day. Now, there's different advantages and little bits and pieces for all of these that make them different choices better and for different things. But when it comes to spatial data, a lot of these have very, core functionality across many of them. They have, your core set of spatial functions. Some of them have extended capabilities. As you can see here, they have these spatial extensions that you can add in, even into Snowflake, which supports Apache Sedona functions within Snowflake, and you can run those there through this package called Sedona Snow. So they have core spatial functionality as well as extended spatial functionality that other providers have put into those. So you have to take a look at what you want to do there. A lot of this is, basically driven by who your cloud provider is or your organization is picked. So there's a certain amount of this that you don't get to choose, but ultimately that's sort of what you do there, is you can pick these cloud services and go from there. So if you're interested in learning the very specific differences between these data warehouses, just let me know and I can break those apart. I'm kind of looking to see if anyone wants me to go deep dives into these topics, but would be happy to do so. So let's jump into the sort of the Apache Spark based ecosystems and talk about those, specifically Apache Sedona, Wherobots, and looking at Databricks and the spatial support within that ecosystem. Now, these are all very similar distributed computing systems, right? When I say distributed computing, and it's a little bit different from what you'd think of the data warehouses in that it's very clear how the data is separated and the compute is separated from each other. In these systems, you effectively have data that's stored in cloud storage, right? You could think of that as a set of files on your computer, but in this case, it lives in the cloud, in Amazon Web Services, and Google Cloud, Azure, or one of the smaller providers. So you can think of any of those where that data sort of lives. And then the compute is being brought to there and spun up at a specific time, and you're given a set of basically what's known as a cluster. Now, if going back to DuckDB runs on what's known as a single node, aka that's this node on your computer. You can think of your computer and the CPU on your computer as a single node. In a distributed ecosystem, there's multiple things being brought to that, or multiple compute instances or clusters. Now, instead of it running one job from start to finish, it's actually taking that job and splitting it up strategically, distributing it to all those nodes, and then reassembling it on the back end. So it's kind of like this very fast assembly line type of process. And within the Spark ecosystem, you actually get a lot more control over how this happens than you would in a pure data warehouse system where that's being sort of abstracted away from your decision making. So you actually get a lot of control over which data goes to which node and how you construct that. And depending on the scale of your process, this is actually very advantageous because you can control all those different elements, split it up efficiently, and make possibly the most efficient pipeline, and even ultimately save time and energy and even money within that case to do that different system. So let's break apart a few of these different technologies and talk about that. Now, I'll start with Databricks. Databricks is the most well-known, I guess, Spark implementation. There are Spark services that are provided on the different clouds. So there's Dataproc in Google Cloud, there's EMR in AWS, Azure has one, I can't think of the name right now, I think it's Synapse. But ultimately, there are these different services. But Databricks is kind of its own service. It provides the notebook to actually run and execute the code, the Spark interface to actually spin that up, and then different optimizations and sort of enterprise level things that you would want in terms of security and access and all of this different stuff, data sharing, data cataloging, you name it, it gives all the bells and whistles that you would want with that. So Databricks basically was built by the founders of Spark. They took their open source project, built a commercial product around it, and allowed you to use that. The only downside, I would say, is that there hasn't been much dedicated, or nearly any, I should say, dedicated spatial functionality within Spark or within Databricks for a long time. They've just sort of recently launched some of these new tools. They previously only supported the H3 indexing ecosystem, but now they've launched some very specific tools that live within that. But it's limited, right? It's not as scalable as you can go. So usually what you see most times is people running Apache Sedona in that Spark ecosystem. So, in that Databricks ecosystem. So let's then pivot into what Apache Sedona does. Now, Apache Sedona is, kind of like if you think of what Postgres is to PostGIS, Spark is to Apache Sedona. Now, Sedona can run on multiple compute instances. It's effectively the functional framework to work with spatial data. And this includes both vector and raster data, and allows you to do that in that parallel processing distributed computing environment that I just discussed earlier. And out of all the data warehouses and the distributed computing, big data computing systems I've talked about so far, Apache Sedona has the most functionality. And out of all of them, it's one of, I think, only two between PostGIS and Sedona that actually supports raster data, which is interesting and important. Some people don't like working with raster data in a SQL-based environment, but the thing is that you can actually use Python-based functions within Sedona as well. So if you don't like SQL, you can use that and run those different things. Now, what Wherobots does is it's basically very similar kind of story to Databricks. It's the folks that started Apache Sedona, and then they built a commercial product around that. The thing that makes it different is that it is its own unique compute environment, and it's probably the only one that's optimized for geospatial data, right? So it runs anywhere from 20 to 60 times faster than, Sedona on just a generic Spark instance, be that the cloud one like the EMR or AWS EMR that I mentioned, or Databricks as well. So it can run significantly faster for spatial workloads and use less computing power, which is time and cost savings to you as the end user. In addition to that, it adds a very important concept, which is this concept of a lake house or a data lake house. Now, a data lake is just a collection of data in cloud storage. That could be images or files or PDFs. In this case, we're talking about tabular data in most cases, things like JSON, CSVs, or in the case of these big data systems, that's most times going to be in the Parquet or GeoParquet format. And a data lake is just that collection of data. Now, what a lake house brings to that is this sort of data layer that allows you to treat it like a database or a data warehouse. So what's really unique about this is that it has a very lightweight schema from usually one of two tools. There's Delta Lake, which is coming from the Databricks ecosystem, or Apache Iceberg, which I think is progressively starting to be the winner in this case. Now, neither of these have spatial support. Now, Wherobots is that it added this spatial functionality into Apache Iceberg. It is not in the full open source Apache Iceberg version as of the recording of this, but it adds spatial functionality, aka the geometry column onto that, and allows you to read that. So when you're in Wherobots, it actually looks like just a regular table, and you can write things to this data lakehouse, as it were, and go from there. Now, the difference between a data warehouse is, and I would say a lakehouse is the level of management around that. A data warehouse is kind of managed for you. If you think about, BigQuery or Snowflake or these tools I mentioned, they kind of manage all these things for you, and it's kind of that management's abstracted away a little bit. You don't have direct access to the storage. In a lakehouse environment, I can go into my cloud storage bucket, be it Amazon S3, for example, and see all the files that are there and the schemas and everything that's there, but I can also access it in my notebook in my distributed computing environment and treat it just like a normal table would. Now, on top of this, what Wherobots offers is the ability to connect to and basically create a lakehouse for raster data that lives somewhere else. So take, for example, all this data on AWS that's free and openly available. These are cloud optimized geotiffs. I can reference these files as out of database rasters, never move the data, of course, and these are lots and lots of, sometimes terabytes of data in image format, reference them, and then when I run my query, I can just pull the parts over cloud storage that I want. And what's really advantageous about that is since it's in AWS S3, it's living physically most times in the same data center as your data that you're running into. So you're basically not trying to transfer something over the internet from who knows where it's actually, physically located. You're in the same data center. So if all my data is in the US West 2 AWS data center, it's all in this physical building somewhere in Oregon that maybe I'll find a map of it if I can, but it may be top secret. I have no idea. I should note that going forward, a lot of these data warehouses are supporting these data catalog services like Apache Iceberg, BigQuery, and Snowflake most notably support these. Here's another video if you want to look at how I used Apache Iceberg tables from Wherobots in Snowflake and directly connected all that to QGIS. So more and more, I think you'll see these data warehouse systems, actually adopting this lake house or data cataloging architecture and using that more and more because people actually, what we found out, want more control over their data. So I would expect to see that more often. And frankly, it's just a lot easier to have that data living in cloud storage than to pull a bunch of files and batch push them into some data warehouse. It just makes things easier, in my opinion. So jumping into some of the distributed query engines, the one that I want to focus in on most is Trino. Now, Trino is a secondary version which sort of rolled out of PrestoDB. Now, PrestoDB is a distributed query engine. What does that mean? Is that it gives you one place to write SQL, but connects to multiple sources. So I can connect to storage from cloud storage, even things like Apache Iceberg, but I can also connect to tables from Postgres and all these other databases and data tools that I might have in my ecosystem. Imagine you're in a very large company, and basically where PrestoDB got started was in Facebook at the time, now Meta, and they have all these different data systems, and they wanted one single query interface to read that, and that's what PrestoDB was. Now, there were some splits at some point in time, I don't know the exact history, where Trino basically moved off into its own open source project and allows you to do that. So it's a distributed query engine, and of course it has some spatial capabilities within that. It's very nice for data that's already prepared, but for data processing, it can certainly be limited because it doesn't have that scaled out computing that I mentioned. It's a distributed query engine, not a data processing or distributed compute environment like a data warehouse or a Spark-based environment like Wherobots or Databricks. But all that said, I think I see more and more organizations starting to adopt these tools. It hasn't really made its way too much into the spatial space yet, but more and more I can see this becoming something that people start to use and do very lightweight spatial queries on, maybe creating points, maybe doing some very simple point and polygon analysis, stuff like that, but nothing too heavy. I actually see there's sort of this convergence in terms of that type of data processing happening in tools like Sedona and Wherobots Wherobots and even Databricks, some of the data warehouses, and on the lighter end in DuckDB and places like that. But the thing that all of this has in common between looking from DuckDB into data warehouses, Spark-based environments, and then also the distributed query engines is it all centers around Parquet files. And I think increasingly you'll see it using those data catalog services as well, using more and more of things like Apache Iceberg. So that's an important topic I want to get more into. So if you're interested in that, please go ahead and let me know. There's two other groupings I want to quickly talk about before I wrap all of this up. They're the GPU accelerated databases. This is tools like Heavy AI, Kinetica, and BrightLight. Now, these tools are basically databases and they throw GPU power at them. Now, GPUs are incredibly, incredibly powerful. That's what's used for doing machine learning. That's what's used for performing, raster inference and some of these very large scale, imagery analytics on anything really, but also for large language learning models. And that's why you see the stock price of NVIDIA shooting up over time because they make really good GPUs and people want to buy them because of it's the race to the who can build the best large language model, and that's what people are doing. Now, GPUs give a ton of power, right? You can do very instantaneous queries on lots of data. The problem with these engines, in my opinion, is that you have to have them up and running all the time. They're not separated. These compute and the storage are in the same place. Compute being the GPUs, and GPUs are not cheap. It takes a lot of money to run these. So if you need this thing on all the time to answer questions, it's going to be very expensive. So if you do need this, that's the case. You just know what you're getting into. Very, very fast, probably one of the fastest out there because it uses a lot of machine power. But unless you need to, basically have an instantaneous result to query billions and billions and billions of records and do these things right away, that might be a good choice, but if not, I just don't see a lot of applicability to them in the space right now. Finally, I want to quickly touch on a few other tools that I've seen over time. Some of the ones that I think are most interesting are Apache Pinot, which is basically looking at analytics, but for end users. So if you think of, opening up your Uber Eats app, you can see here that it shows that so-and-so ordered this nearby you at this given time. It's analytics for millions of users. And it's really cool because I've seen this use case a few other times where someone's doing very lightweight spatial queries on a database like this. Pinot is the toolkit that actually runs analytics in LinkedIn, in Uber Eats, and some of these other applications. So it's very scaled analytics outward. Not great for data processing or anything like that, but it has some of these interesting use cases for commercial applications that are going to thousands or tens of thousands, hundreds, millions of users at the end of the day. And it, of course, has spatial queries, so it supports some of those tools as well. So if that's something you need, you can get started there. Another one that pops over time is this tool called Clickhouse. It's a distributed sort of query interface that's also very, very fast. I know it has spatial capabilities, and I think a few people have mentioned to me over time, but honestly, the spatial, when I look at the documentation, it's pretty limited. So yes, it's fast. Yes, it's very powerful. Unless you're doing a very focused set of spatial functionality, it seems a little bit difficult, and you have to write a lot of the functions yourself. Writing something like an ST-intersects does not seem very straightforward based on what I'm reading in their documentation. If you want to prove me wrong, go ahead. I might be totally wrong with that, but this is at least what I'm reading on my end. So that's my view of Clickhouse. So those are these other tools that I sort of mentioned. There's lots of other tools I may not have covered on this. I didn't cover all 50, of course, but I want to give you a sense of how this space is breaking out. So what does this all look like? Let's take a quick look at how these things rank on that ranking from transactional to analytical, and well as distributed processing. So first, let's go ahead and throw the relational databases on there. You can see here where these different ones rank out. It's hard to say which ones have more or less computing power because you, as the user, kind of choose that. But in terms of all these spatial components, I'll make the image bigger. And obviously here, PostGIS is the one that's going to have the most spatial functionality. So that's why I kind of put it right at the top because it has all those different tools in it. You can look at the commercial ones as well. They have varying, levels of spatial capability, but ultimately, I think if you're looking at spatial, PostGIS is the one, and as probably the best relational database for those types of things. Putting on DuckDB here, you see it has a large and growing amount of spatial functionality that's tied into it, and it falls more on that analytical side. Scale is one of those things where it's kind of hard to pin down because if you have a larger computer, you can run more things with that, or you can use a sort of distributed computing service like MotherDuck to scale that. But ultimately, it's not like infinitely scalable, but it's very scalable for lightweight analytics use cases, so that's why I'm placing it here. Now, here's well placed at data warehouses. You can see here by the size of the icon which one has more or less spatial functionality. It's hard to say which one because some of these can kind of scale quite large. Some of them you have more control on, but they all fall in this analytical quadrant. And they definitely, in terms of scalability, have varying levels there. Some of it gives you more user control or less, so it's hard to kind of express that part within this, but at least that's there. Now, talking about when we're looking at the Spark or distributed computing interfaces there, let's dive into those. And of course, Apache Sedona and Wherobots are going to win out because they have the largest amount of spatial support for these pure lakehouse or distributed computing, Spark computing, whatever you want to call it, interfaces here. So those are the ones that are going to win out. Databricks, of course, has it. It's growing, so it's adding more and more over time, but it is not the winner in my book compared to these other two that I'm looking at here. Distributed query engines, looking at Presto, and Trino, that's where I'll place these here. There's a few others as well. You could look at Apache Hive, Apache Drill that are here as well. And I'll put the, GPU accelerated databases here to talk about what they can do as well. Very analytical for the most part, not transactional. A big downside here is these are going to cost you a lot of money. If you do need that very responsive thing, some use cases that's the case, and if you want to do that, but hey, like I mentioned, it could cost you a lot. And here's all place, Apache Pinot and some of these other tools. There's a few others I didn't get to mention in this video that I would talk about, some of the sort of NoSQL databases like MongoDB, even things into like some Elasticsearch and Cassandra and some others. There's kind of an interesting subset that I would look at. They're not like specific to spatial in a way. Some of them have spatial capabilities, but they're much more focused on like search right there. And it's hard to kind of compare that along these lines. They're not distributed processing systems, but they're maybe more meant for finding very specific things at very specific times, and that's what they're good for. Of course, they're not pure SQL either. You can't just write pure SQL against these either. That's why you get this label NoSQL. So I kind of kept them out of here for now, but I just wanted to give a quick acknowledgement and tell you what those are. So that's my overview. I hope you gave you a good breakdown understanding what the different pieces are that go into all of these. If you have any questions, you know where to put them, drop those down in the comments, and I would love to make more videos like this. So if there are specific tools that you want me to focus in on and do a more detailed dive, let me know, and I will be happy to get to those. So yeah, thank you for watching, and I'll see you next time.